Welcome back, everybody. In the first part of Chapter 7, we talked about this idea of enthalpy, calculating enthalpy from breaking bonds and forming bonds, and using enthalpy as just a part of the recipe. And enthalpy, it turns out, for our purposes, is just kind of a smart aleck way of saying heat. The next big idea in this chapter looks at another kind of energy and another consideration. So I'm going to start off with basically looking at enthalpy again and thinking about, well, what does nature prefer to do? And remember, nature is lazy. Nature is always, it has some reactants at a high energy condition, and the products would be at a lower energy condition. We think nature always wants to do this. Nature's always wanting to go from whatever it's got to go to a lower energy. I could maybe draw a little graph here. And if I thought, well, H was kind of over here, and we could say maybe this is like a reaction. Something's going to happen. And I could think, well, my reactant heat is here, and my product heat I'd measure down here. Well, I would find that this thing would want to happen. Nature said, yeah, I'm going to do whatever it takes to turn those reactants into those products. And we'll draw a picture of that later. So we could say, okay, if we're looking at enthalpy, enthalpy wants to go downhill. We're going to keep saying, well, this is sort of what nature prefers, or this is favorable, or this is spontaneous. Well, nature wants to go downhill. Nature wants to do something that gets rid of heat and brings everything down to a lower level of energy. Here's something we hadn't ever talked about before, but nature does this. Nature's lazy, and nature is a slob. Nature loves to take things that are orderly, compact, and neat and turn them into disorder, diffuse, spread out, messy. We see that again and again and again. Now, this messiness is called entropy, and the variable we usually use is S. And what we want to say is nature usually gets messier. Nature would like to go downhill in energy because it's lazy, and nature would like to increase the messiness, the diffuseness. So here's what nature's saying. I'd like to lower it, and I'd like to make a mess. Well, this brings us to a big idea. The second law of thermodynamics says, for any spontaneous process, that just means it happens. Once you start it, it just happens. I don't have to add anything. I have to add a reactant. It just happens. Could be a reaction, could be a physical change, but that will just happen sort of on its own. And anytime I notice that, here's what's going on. And this sounds sort of smart alecky too, but the entropy S of the universe, that sounds like a big deal, of the universe increases. That's all that means. It says, anytime I see something happen, something melts or something freezes, if something burns, if something reacts, precipitates, whatever it is, somehow the messiness of the universe has increased. So we could say, well, positive delta S of the universe. Now, we're not going to look at the universe. We're going to say, well, what if I just look at my little reaction happening in a flask or a reaction vessel or something like that? So, let's look at this. Page 7.10. And this is very just sort of intuitive. A solid going to a liquid is positive delta S. What do we call that, solid to a liquid? Well, we say, well, anything melts. Nature loves for things to melt because that solid is orderly and compact, and it becomes disorderly and spread out. Here I have a solid going to aqueous. Well, I thought about this a bit, but really it's just dissolving. I better say it like this. I have to be very careful. A solid dissolving. This does not apply to gases. So anytime I get a solid to dissolve, okay, that's getting messier. Example 3 is a little more subtle. What I want you to do is look at the gases. Here I've got no gas, making a solid and a gas. Here I've got gas going to a gas going to a gas, and you might say, well, I don't see any pattern. One has gas, one doesn't have gases. So you might stop the video for a minute and think, what's going on here? All right, here's what's going on. In this reaction right here, I've got 0 moles of gas going to 3 moles of gas. And stop the video and think about that. Here I've got 3 moles of gas going to 5 moles of gas. 3 moles gas going to 5 moles of gas. Now that doesn't make sense. Stop the video, look at that for a second. So it really comes down to this: increasing the moles of gas. So if I increase moles of gas, and these are just common things that we see. Like, oh yeah, melting. Oh yeah, solid dissolving. Generating gas, generating more gas than you start with. Those are sort of some common conditions that we can say nature likes to do this because it increases entropy. And the big idea is, does stuff get spread out? Does it get more disordered? Does it get more sort of messy? I could come down here and look at these problems and think about these processes. Giant molecule broken up in the body like a starch. This is thousands, tens of thousands, hundreds of thousands of atoms get broken down into little sugars that only have like maybe 20, 25 atoms in them. Well, big, orderly, all stuck together, breaks down into lots of little molecules that can go all over the place. That sounds like it's becoming more messy, increasing entropy. Now you might stop the video and look at those two. I think you can figure those out. All right, stop and figure it out? Yes, you did. Steam condenses, I can think of this as a couple of different ways, on a glass surface, so I get a little droplet there. Well, it's gone from something that was large to something small. That looks like a little less messy. And you could think of it as, well, I'm going from gas to no gas. So that looks like it's decreasing messiness, decreasing disorder. And this one's pretty easy. 3 moles of gas going to 2 moles of gas. No, that's not more messy. That's less messy. That's a negative delta S. Let's look at page 7.11. So we have said nature likes to do things that are exothermic, get rid of energy, and nature likes to do things that increase messiness. So when I look up here, I see, okay, dang, that's endothermic. That requires heat. That's unfavorable. Now, the delta S for this process, however, is increasing entropy. Nature's happy about that. Now, there's the process we're talking about. Solid water going to liquid water. Well, that's just melting. That's just ice melting. So does ice ever melt? Well, yes, of course it can melt. You've seen it melt. Well, under what conditions? Well, when it's above the melting point. Above melting point. So somehow at above the melting point, it doesn't care that the enthalpy is unfavorable and that the entropy is favorable. Now, when would that not happen? Well, below the melting point. And enthalpy is still unfavorable. It doesn't want to do it. Entropy is still favorable. So what haven't we considered? Well, temperature. I'm going to use T for temperature. So, okay, yeah, does it have to add energy in to make it happen? It doesn't like that. Does it get to let energy out? It's that. Does it get messier? That's happy. Does it get less messy? It's unhappy. And when does it make that decision? Well, it comes down to temperature. Now, by the way, this, for our purposes, has to be in kelvins. It's an easy conversion, but... So here's what it turns out. It turns delta H, the change in enthalpy, minus the temperature times the change in entropy. And we can look these numbers up. They're right there. 6 kilojoules per mole, 22 joules per mole. If that calculation is less than 0, we say it's spontaneous. When we measure those things, we can tell you, oh, is this whole thing, is the net going downhill, or is the net sort of going uphill? If nature says, yeah, I'll balance all these things, if you give me an opportunity for this quantity to get less than 0, I'm happy. Well, that quantity is delta G. We often call it free energy. It's Gibbs free energy. Gibbs free energy. So sometimes we'll say Gibbs, or sometimes we'll say free energy, Gibbs free energy. Delta G is the thing we want to know, and that just is equal to delta H minus T delta S. So spontaneity, when that's less than 0, when delta G has a negative value. So now I've got one thing I can measure. Temperature, well, I've got 3 things to consider that gives me one thing. Heat coming or going, the temperature, and is it getting messier or neater? I can do those calculations, calculate delta G, and make decisions about whether or not it's going to happen. Well, it gives us some new terms. Remember when delta H was negative? We called it exothermic. When delta H was positive, we called it endothermic. Well, we have something similar here. We say that looks sort of like it's going to be exothermic, exergonic, and endothermic becomes endergonic. Is that like a Star Wars planet or something? Okay, so there's the math. That's what we're looking for. Now we have a new term. Ergonic just means, oh yeah, that'll happen. You get it started, it'll keep going. Endergonic means nope, it will not do it unless you do something else to make it happen. All right, let's do one math calculation, 7.12. It's pretty easy. So I've got a process, C2H4 plus hydrogen give me C2H6. And we don't do it in this class, but you can actually find the value for delta H. There's a couple of different ways. We could calculate delta H from the bonds. We could look it up in tables. There's a number of different ways to do it. But there it is given to us. There's delta S. Delta S you can find in tables. You can look up every compound, and there's a way to calculate delta S for the reaction. Reminded me that, oh yeah, kelvins is degrees C plus 273. There's the temperature. Now, there's one messiness here. It looks really straightforward. You go, well, it's just that. So I go, well, that equals minus 137.5 kilojoules minus 25 plus 273 kelvins. Now I might stop and say, wait, why did he add the 273? Here's my delta S, minus 120.5 joules per Kelvin. Kelvins are going to cancel. I've got joules here, but notice what I've got over here. Kilojoules. Very commonly done that way. Enthalpy is kilojoules. Entropy is joules. So here's the easy way to do it, I think. Here's what I always do. I just say, okay, minus 137.50 joules. Whenever it's kilojoules, I go, okay, I'm just going to multiply it by 1,000. Makes my life easier. It's fairly easy to do. I just move the decimal over 3 places. Now I've got 298 kelvins times minus 120.5 joules per Kelvin gives me minus 137.5 joules plus, review that algebra, 35,900 joules. I'm going to do the math. What do I get? About 102,000 joules. Probably round off to 3 sig figs, or minus 102 kilojoules. Is that spontaneous? Yes. So here's the answer to A, and B is yes. Delta G is less than 0. That's it. And you don't have to memorize that equation. I'm going to have to figure out how to give you that equation. But yeah, you don't have to memorize that equation. Well, it's open book, open notes at this point. So, okay, that's pretty straightforward. Now, where it really gets interesting is when we don't do calculations. Using that equation without actually doing any calculations is way more interesting. So here's what I'm going to do. I'll remind us, we've looked at this a couple of times. Gas. I'll draw a little flask or something there. And my solid. And I want to think about this direction. If I melt, or I vaporize or boil, or I go from a solid to a gas, sublimation, am I adding heat to that, or is heat coming out? If I had looks like a stick of butter, an ice cube, whatever. If I wanted to melt that, I've got to add heat, right? That is endothermic. Positive delta H. And in this little silly diagram and the way we're going to sort it out, that's where I always start. Because we all know, oh yeah, to get something to melt, to get butter to melt, I have to add heat to it. That's endothermic. I had to add heat. Now, the other one's a little bit trickier, but what's happening to entropy here? I've got a nice orderly solid, slightly more disordered liquid, and then it's completely disordered as a gas. That's increasing messiness. That's increasing entropy. Now, everything we do in Chapter 7, when we do it in reverse, all the signs change. If I think about condensing or freezing, I'm going to say, oh, wait a minute. That must be the exact opposite. Every time we do anything in the opposite direction, physical process, chemical reaction, when you switch directions, all the signs change. So this over going this way was endothermic. Going this way is exothermic. Well, if it got messier going that way, it gets more orderly, less disordered going the other direction. And this sort of makes sense. And I think if you start with this, it'll help make sense. Now, I'm going to make a little table at the bottom of the page here. Now, what I want to do is use the equation and do no math whatsoever. This is what's valuable in the real world. We said that vaporizing, melting, subliming required heat, but things got messier. So if I think about my delta G now equals some positive value minus T times some negative value. Well, that's no good. We don't want that positive thing to be dominant. That makes delta G a positive number. This over here Oops, sorry. Let's fix that, of course. We just drew the picture. Vaporizing, melting, subliming required heat. It was endothermic, and it got messier, which means this term over here, my delta S, is positive. Well, what I have to do is think about how do I make that whole thing negative by only changing T. That's positive. This part right here now is negative. How do I make this negative part bigger? Make T bigger. So this happens, is spontaneous, when the temperature is high. Without doing any math, you could plug in numbers if you want, but you go, oh, that number is positive. Oh, this term over here is going to be negative. Negative times a positive. And so remember with kelvins, there's no negative temperatures. So the bigger the T, the more negative that becomes, and the more favorable it becomes. And that makes sense. You're trying to go in this direction, melting, boiling. You want that to happen at higher and higher temperatures. Now, what about going in the opposite direction? We said, well, when we condense or freeze or deposit, delta H is negative. Oops, I'm going to make that in red. No, I'll leave it like that's what I'm going to. Delta S is negative. Well, unhappy, happy. I better do these two. Unhappy, happy. Well, but these processes occur. Delta G equals negative delta H minus T times a negative delta S. Well, minus a minus, this part over here is going to be positive. We want this part to be as small as possible. That part's helping us, the delta H. So these happen at relatively low temperatures. And that makes sense if I'm trying to condense or freeze. Oh yeah, I want that to happen at low temperatures. So much more interesting than doing the math. Now, in the real world, we sometimes encounter this. I've got an exothermic reaction. That's good. And I've got a reaction that's getting messier. Looks like smiley face to me. But let's do some conceptual math. Delta G equals a negative delta H minus T times a positive delta S. This part's negative. This part is always negative, no matter what T is. So I can say, oh, if you've got that, we could say all or any temperature. Exothermic and getting messier, cold, hot, it doesn't matter. It's going to happen. Now what about here, the last case on this page? It is endothermic, no está bien, and it gets less messy. Doesn't like that either. Well, let's look at what the math would be. Delta G equals a positive delta H minus T times a negative delta S. That becomes positive, that becomes positive. This is spontaneous at no temperature. Now, it doesn't mean it won't happen. It just means you can't put this together in a beaker, walk away, and it happens. You've got to do something else to make it happen. So this, I think, is the most interesting thing about this part of this chapter is under what conditions do things happen? Now, we can do the math. There's a problem or two like that, but that's the interesting part. Okay, the next section, we are going to completely change gears. We are going to forget all about this, and we're going to think about how reactions happen at the molecular or atomic level. What has to stick to what? How does that actually happen? And what does that mean about what do we observe for the reaction? All right, folks, I will see you at the next lecture segment. Thanks for your patience as always.